now we want to look real quick at the inverse part, inverse transform. Now, there actually is one defined in terms of an integral, but we aren't going to use that. We're going to use a table. And so on page, whatever it is, page 327 of your text, there is a table, and they give us these exercises of finding inverse transforms. And the first one, they say, well, in A, f of s is equal to 2 over s squared. Now, what we have to do is we have to go looking for that sort of thing in the table. And if you look at the third line down, what you find in the table is that t to the n, where n is an element of the natural numbers, we have our 0, 1, or well, 1, 2, 3, 4, 5, and so forth. We've got these natural numbers. It says that its Laplace transform is n factorial over s to the n plus 1, and s is greater than 0. Okay, so there's a plus. And so as I look at that, I think, oh, okay, well, if we have that n plus 1 is equal to 2 because we have s squared here, then that would mean n is equal to 1. And in that way, what I know is if I have 1 factorial over s to the 1 plus 1, that inverse, f inverse then is going to be t to the 1. Well, except I don't quite have that. I have a 2. Well, remember our linearity property, and so what I'll do is I'm going to take my, oops, quit that. I'm going to take my 2 over s squared and think of it as 2 times 1 factorial over s1 plus 1. Pretty sloppy ones there. But then that says that my f inverse, now notice I don't have an equal sign here because these two expressions are not going to be equal. One's in terms of s, the next one's going to be in terms of t. They are not at all equal, so I'm using an arrow to signify my inverse transform here. And so I have 2 times t to the first, okay, or 2t. And there's I've done my inverse transform. And you could always check it by taking the Laplace transform of 2t, and hopefully you would indeed get 2 over s squared. So then they give us a b. Let's see what we've got with that one. And their b, they've got the same sort of thing. They have f of s is 1 over s to the fourth. Well, and from the previous item, again, remember we had n factorial over t to the n plus 1 is the form we're going for, or sorry, s plus 1 is the form we are going for, and that, again, using our inverse gives us t to the n. And so I look at this and I say, well, okay, I need to find my n, but n plus 1 is 4, so n equals 3. Well, so I need a 3 factorial up here, and so I just write it that way. I've got 3 factorial over s to the 3 plus 1. So there's the form I need. Now, but I don't, up here, that is not a 3 factorial. Well, it's a 1. I can fix that. Just I multiply it by 3 factorial, divide by 3 factorial. So I have that times that. Now I follow my inverse Laplace transform, and I have my 1 over 3 factorial, and then I have my t cubed. And so there's my solution there. But you see, it's a bunch of fancy arithmetic, algebraic kinds of things. Is what, you know, that's really the key here. This is not calculus at this point. We're doing table lookup and working with a lot of algebraic concepts. Finally, in C, they say our f of s is equal to 2 over s minus 3 quantity squared plus 4. Then you scan the table and you look around to see, okay, what do they have? You know, I see in that table I see a 1 over s minus a. Well, you know, I've kind of got something like that. But no, I don't really see anything that looks really good for it. Now, looking farther down, I do see, I see something that says e to the at cosine bt, right? Cosine, no, sorry, sine bt. Got to look at the right thing. That, through my Laplace transform, when I do that, I get b over s minus a squared. That's looking good. I see a s minus 3 squared over in my thing there. Plus b squared. And that is good as long as s is greater than a. We don't usually have to worry too much about that domain, but nonetheless it is there. And so as I look at this, it looks like actually this is perfect in that if I let a be 3, that works out perfectly, and b be 2, that works out both top and bottom. Now, the top I'm not worried about because I can always multiply or divide by constants to make that top work. I was worried about the bottom, and and I have, so I need b squared to equal 4, and so b is 2. I'll take the positive square root of that. And so with that, that was nice because once I've defined that, then I take that 2 over s minus 3 squared plus 4. I've identified my a and b for the table. So here's my Laplace inverse that I'm using, and according to that, since a is 3, I have e to the 3t, and then b is 2, so I have sine 2t. And there's my inverse Laplace transform, but I do it from that table lookup, and I just look for something that looks reasonable. And as you might guess, this is where it can just get really nasty in that there's all sorts of algebra I can do to things to change them around. I didn't have to do anything to this one. We had to do a little bit to that one, and the first one, very tiny bits of just kind of factoring some things out. But it can get pretty rough to try to find this inverse. But that's the idea, is that once we get to something, so for instance, we might get to an answer that looks like that, 2 over the s minus 3 squared plus 4, and we say, well, okay, well, we want to go back, and, well, how do we get back? And that's where we'll use these tables. But we'll also use Sage Sage Math can do a lot of Laplace inverses because, again, they're just really coming from tables. So we'll use that to help us. But that's the idea of finding these inverse transforms, and that kind of hits the big ideas of the introduction part in 6.1, and so you're hopefully ready to start diving into the homework with this. All righty, we'll call that good.